This video provides a tutorial question on a mixing tank. So the reader is reminded that what we're doing here is providing a tutorial question with the intention that students try this by themselves before they later on go and look at the work solution provided. So please make sure you do that. Pause the video at the relevant point and then try the question by yourself. So here's the question. We've got a mixing tank and we're going to assume that the tank is well mixed. The solvent and the product A have got the same density and the flow in is constant and equal to the flow out. So the thing that we're most interested in is what impact does a reaction have on the molar concentration in the tank. So we're going to assume there's a reaction and the chemical we're interested in, A, is consumed at a rate Ra, where the units Ra are moles per meter cubed per minute. Okay, and here is the expression for Ra, and you'll notice it's a non-simple expression, so it's 0.1 times the concentration plus 0.05 times the exponential of 0.1 times the concentration minus 1. Now we're given some data: the volume of the tank 3 meter cubed, the flow rate 0.15 meter cubed per minute, and the concentration of the inflow 1.2 moles per meter cubed. What we're going to do is apply a step increase in the molar concentration of the input, where the step increase is 0.3 moles per meter cubed. What we'd like to know is how does the concentration in the tank change when we apply this step. We will assume that the system was initially at steady state before we applied the step change, and the technique we want you to use is to solve for Ca and remember to use deviation variables. So this is the point at which you should pause the video and have a go at this question by yourself before you look at the worked solution. So then, as there's a reaction, we note that the steady state concentration in the tank will not match the concentration of the inflow. And what we're going to do first is say, well, what do we want to balance? Well, the obvious thing to balance is this component A. So what have we got? What's the rate of change of component A in the tank? So we've got the volume of the tank times the concentration, which was per meter cubed. So we've got the rate of change of concentration with time, dCA dt, times the volume in the tank. How much A is coming in? Well, we've got the flow rate times the input concentration, and then we've also got the flow rate minus the output concentration. So that's how much of this component A is coming into the tank minus how much of the component A is going out of the tank. But A is also being consumed, and you remember what the units of A are, so we've got Ra, we have to multiply by the volume in the tank. So that's our balance in terms of component A. Now, what you could do next is you could say, oh, well, I've got some more numbers here that perhaps I could substitute in. I know what R is, so let's do that. V dCA dt equals F into CaO minus Ca, and then minus, this Ra was quite a lengthy term, 0.1 Ca plus 0.05 into e to 0.1 Ca minus 1, and all of that lot times V. Now, what might I want to do next? I might want to say, okay, let's do a balance at steady state to see what's happening at steady state. Well, at steady state, we've got dCA dt equals 0. So therefore, if I also divide through by V to make life a bit easier, I'm going to have equals F over V into, have I done that the right way? Sorry, I've divided by the wrong thing there, I do apologise. What I'm going to do is I will just leave as it is for now, so we don't make the same mistakes. We've got F into CaO minus Ca minus V into 0.1 Ca plus 0.05 e to the 0.1 Ca minus 1. So there's our balance at steady state. And you might look at that and you might say, this is going to be fairly tricky to solve. We can put in some of the numbers, and you'll notice I've given you the numbers over here because they can be helpful. So we know that V is 3 and F is 0.15. So if I divide throughout by F, so what I'm going to do is I'll cross it with a red so you can see what I've done, and I'm going to put it down there. Then what I get left with is CAO minus CA minus, now V over F is going to be 20. So if I put 20 times 0.1, that's going to be minus 2 times Ca. 20 times 0.005 is 1, so you're going to get minus e to the 0.1 Ca minus 1. That's now beginning to look a little bit easier. So remember, this is the steady state. I haven't put the subscripts in for now, because it will make it messy, but that's my steady state expression, so I can use this to work out where the system is before I apply my step change. Okay, so we need to solve this expression, and you're thinking, yeah, but it's a bit messy, I'm not quite sure what to do. So the first thing to do is to notice that if Ca is small, then e to the 0.1 Ca is actually equal to 1 plus 0.1 Ca plus lots of small terms. So I've done a Taylor series expansion. You can do it another way if you like, but an exponential with a small exponent can be approximated by a straight line. So that's what I've done there. Now, if I substitute that in, you'll remember, and I'll put it at the top here, we had a term e to the 0.1 Ca minus 1, and you can see that this is going to be approximately 0.1 Ca. So that's going to make our life a lot easier. So if I go back to the previous page, look at this blue box, and look at what I had in here, I'm going to be able to replace that by 0.1 Ca by doing a simple linear approximation, which is valid as long as 0.1 Ca is small. And clearly, if you read the data at the start, we had Ca which has values of around 1, so you're talking about numbers of e to the roughly 0.1, so the approximation is valid. So what I can do now is I can rewrite my steady state, and I'm going to get CAO, and now I'll put in the S, CAOS equals CAS plus 2 CAS plus 0.1 CAS, or in other words 3.1 CAS. So I can work out now what the steady state will be. Now we were given that CAO, S equals 1.2, and therefore CA, S equals 1.2 over 3.1, which equals 0.39. Next, we put in our deviation variables. Now, whether you really need them here, because we've simplified the model to a linear model, is debatable, but it's good practice to do this anyway. So CA dash equals CA minus CAS, and CA0 dash equals CA0 minus CA0S. So there's our standard deviation variables, and what we can do is we can plug those in to our original differential equation and see what we get. So we're going to do that on the next page. So there we go, a reminder of how we define our deviation variables, a reminder of the model that we've just derived. However, just in case you've forgotten, we've said that this term here can be approximated as 0.1 Ca. So that's what we're going to do hereafter. So what we've now got is 20 into d dt of Ca dash plus Cas equals CAO dash plus CAOS minus 3.1 into CA dash plus CAS. And you'll remember that by definition, this term, this term, this term, they all are going to cancel. So what you get left with is 20 times d CA dash dt equals CAO dash minus 3.1 CA dash. So now we've got a simple approximation for our system and written in terms of deviation variables. So I've rewritten the expression here, but you'll notice the subtle difference is I've moved the CA dash onto the same side as the derivative, so that this is in time constant form, and I've also divided throughout by 3.1, again to put the model in time constant form. So we have 20 over 3.1 dCA dash dt plus CA dash equals 1 over 3.1 times CA 0 dash. And if you read the start of the question, you'll remember we said that CAO dash is going to be 0.3. Now because this is in standard time constant form, I can actually write the solution by inspection. I'm going to get the new steady state, which will be 0.3 over 3.1, and that's going to multiply 1 minus e to the minus t over capital T. Capital T is the time constant, but capital T we know is 20 over 3.1 because we were given that. And if I want to get back to the actual CA, you remember we had the steady state, which was 0.39, so it will be 0.39 plus CA dash. So we've given a tutorial question on a mixing tank with a reaction, and we've gone through the work solution, and we've also used deviation variables, and we've dealt with the nonlinearity by using a simple Taylor series expansion and small